A very good morning. I continue with my class on chemical properties of group 2 elements. The group 2 elements we had already started off in my part 1. Moving to the next important chemical property, which is solution in liquid ammonia. When we talk about a solution in liquid ammonia, you have your metal and a large excess of ammonia. Large excess is referred to by the X plus 1. Your metal will change into a metallic ion, that ion with 2 positive, and your electron would have a negative charge. There will be 2 such electrons liberated. Each, the metal ion as well as the electron, will be surrounded by a large number of ammonia molecules owing to its polar nature. The structure of ammonia molecule is like this with the lone pair. Lone pair, the dipole moment is like this, and these 3 hydrogens also have a dipole moment towards nitrogen, nitrogen being more electronegative. So the next dipole is towards one direction, hence this becomes a polar molecule having both positive as well as the negative charges on it. Via the negative charges it surrounds the metal positive, and via the positive charges it surrounds the electron. And it is this electron which is liberated in the ammonia liquid that makes it conducting as well as a colored solution. Let us talk about the comparison of the ionic character. When I talk about the comparison of the ionic character, I have taken 2 examples, sodium fluoride and magnesium fluoride. Sodium is group 1, magnesium is group 2. Sodium has a larger size and has a lower ionization energy. So the electron transfer to fluorine is going to be easier in comparison to that of magnesium. Therefore, if the electron transfer is easy, automatically the ionic character would be high. Done? The second example is of the same group, calcium chloride and barium chloride. Both calcium and barium are in the same group. Both of them have to lose 2 electrons. But out of calcium and barium, which is larger in size? Barium. Since barium is larger in size, it can easily lose the electrons because the ionization energy is going to be low. If it easily loses the electrons, hence the transfer of electrons is easier in case of barium than in case of calcium. Hence the ionic character would be higher for barium chloride. Moving to the next example, I have lithium oxide and beryllium oxide. Actually the example should not have been for the ionic character because they generally form covalent compounds, but since all covalent compounds do have a considerable ionic character according to the difference in their electronegativities, so I am talking about the ionic character in this case. If we talk about the ionic character, which out of lithium and beryllium, oxygen there is no need to compare because it's common to both, which out of lithium and beryllium do you think would easily give off the electron? Lithium, because of its larger size. Lithium is larger than beryllium. As you go across a period, the size goes on decreasing because of the stronger attractor pull by the nucleus to the last electron. Hence the electron loss is easier here. So the ionic character would be larger in case of lithium oxide. There is another way of understanding it via the Fajan's rules. According to Fajan's rules, we find out the covalent character. And the covalent character is more whenever the charge density is high. Beryllium is smaller as compared to lithium. Also it has a +2 charge, therefore the charge density is high, so it pulls the electron cloud of the oxide ion towards itself, and this is called as your polarizability. The polarizing power of beryllium is higher, so the covalent character increases, therefore beryllium oxide is more covalent while lithium oxide is less covalent or more ionic. Talking about hydroxides of group 2. If I talk about hydroxides of group 2, let us talk about the basic character. Metal hydroxides are basic. Now, which out of magnesium, calcium, strontium and barium is most metallic? The one which can easily lose electrons. What are metals? The elements which have a tendency to lose electrons. So, which will lose the electron easily? Barium. If barium can lose the electrons easily, it is most metallic. If it is most metallic, then the metallic hydroxides are more basic. So when we talk about the basic character, this is the order for the basic character. Basic character increases down the group. Talking about solubility. When we talk about solubility, the 2 terms that come into picture are lattice energy and your hydration energy. The solubility of a salt is only possible if hydration energy is greater than lattice energy. In this case, the the solubility order also remains the same. There is an increase in solubility as you move from magnesium hydroxide to barium hydroxide owing to, as you can see, down the group the size is increasing, so the charge density is decreasing, so the hydration would decrease. Hydration is decreasing, that's fine, that should not promote solubility. But simultaneously, the lattice energy is also decreasing owing to the large difference in the size of the cation to the anion. So since both of them are decreasing, it is found that lattice energy decreases more rapidly than the hydration. Hence, the hydration energy remains more than the lattice energy despite the fact that both the values are decreasing. Hence, the solubility as well as basic character of the hydroxides of group 2 increases on moving down the group. Now let us talk about the carbonates and sulfates. As you very well know, a carbonate is CO3 2- ion. Sulfate is SO4 2- ions. They are bulkier anions. So, since they are bulkier anions, I am going to talk about the thermal stability. How strong is the bond between the anion and the cation? The strength of the bond is dependent on the comparative sizes. If they have similar sizes, the strength of the bonds are strong. So, as I move from beryllium to strontium, the size goes on increasing. If the size is increasing and we know that the anion is large, anion is also larger in size, so which out of them would be a more stable compound? Which has larger cation and a larger anion. So, your strontium carbonate that becomes most stable, the bond is strong, so even if you heat it, it remains stable. So, it is thermally stable. The bond does not break easily. Hence, the order of thermal stability becomes this. Exactly on the parallel lines, when we talk about sulfates, the sulfate ion anion radical is again a bulkier anion radical, and a bulkier anion would be stabilized by a larger cation. So, the bond between strontium and sulfate is stabilest out of the all. Hence, the order of thermal stability in both carbonates as well as sulfates increases on moving down the group owing to the higher stability of larger cation bonding to a larger anion. Now talking about the solubilities. When we talk about the carbonates and the sulfates and we talk about their solubilities, it is found that as we go down the group, if I move down the group, the hydration is decreasing. Why so? Because the size is increasing, the charge upon radius ratio will, size is increasing, so charge upon radius ratio will decrease. Hence, as I move down the group, the hydration is less. But we very well know the lattice energy is higher. If the hydration is less and the lattice is higher, this will not be soluble. So, the solubility order should be this. Done? On moving down the group, we see that the hydration energy is decreasing because the charge upon radius ratio is less. Also, the lattice energy is increasing. So, this is reverse to what we want. When we talk about solubilities, what do we want? We want lattice energy should be less than hydration energy. And on moving down the group, this is not so. Hydration becomes less than lattice. Therefore, solubility will not increase on moving down the group. The solubility increases again in this order. Moving ahead. Anomalous properties of beryllium. The first member of all groups is different from the rest. The properties by which beryllium is different from the rest, the first is it prefers to form covalent compounds. Why does it form covalent compound? Because the size is small and the ionization energy is high. So it would not easily give away the electrons. So the first member, beryllium, prefers to form covalent compounds of the type beryllium oxide, beryllium chloride, etc. Coordination number is 4. Coordination number is a new term. You can relate it to the covalent bonds. Coordination number means how many other atoms are surrounding a particular atom is the coordination number by definition. But in the compounds of beryllium, how many bonds does it form is the reference with respect to coordination number. You can take it to be covalence. Beryllium can only form 4 bonds maximum, including coordinate and covalent. Why so? Because beryllium's electronic configuration is 1s2, the first shell, 2s2, and that's it. You do have a 2p, which is vacant. So in all, you have s and 3p subshells, therefore total of 4 orbitals, which makes it have a maximum covalency of 4. While the rest of the members do have a 3d. Here you do not have anything of the type called as 2d. So only possibility is s and p. So total orbitals will be 1s and 3p. Total of 4 bonds can be formed. It forms bridged covalent chlorides. This we already did when we talked about the bridged covalent chlorides. Your beryllium chloride, if you remember, the structure of beryllium chloride was like this. In the solid state, beryllium chlorides join together via coordinate bonds like this, and they lead to a polymeric unit. So your polymeric unit looks like this. The same is true for magnesium chloride? No, because magnesium does not form covalent bonds. Magnesium prefers to form ionic compound like this. Magnesium has a larger size. It can easily give away its electrons to chloride, therefore leading to magnesium 2 plus and now 2 chlorides. Hence the bond is ionic. So as all the members, all other chlorides are ionic, beryllium chloride is covalent. Coming to the next important property is diagonal relationship. Group 2 members, I have just taken 2 of them, beryllium, magnesium, rest are there. After this you have the transition metals, for which I have left a cap. After that you come to group 13. In group 13 you have beryllium, boron and aluminium. So diagonally we find beryllium resembles aluminium, and there are similarities between beryllium and aluminium. The first similarity is beryllium and aluminium both form a protective oxide layer. This protective oxide layer makes it inert. It does not allow it to react further. The chlorides are soluble in organic solvents. I will be doing the chlorides in detail a little later. But if they are soluble in organic solvent, it clearly indicates the formation of covalent bonds, because covalent compounds are soluble in organic solvents. The last, chlorides in their solid state are bridged structures. What do I mean by that? Chlorides in their solid state are bridge structure is what I mean. Your beryllium chloride, I have already done this twice. The structure of beryllium chloride when in the solid state, each layer beryllium is surrounded by 2 chlorines, but they are bound to each other via coordinate bonds from chlorine due to the presence of lone pairs on chlorine. Hence you have a polymeric unit. The same is also true for AlCl3. Please mind you, AlCl3 has a structure of this kind. You have an aluminium having 3 chlorines. It is a covalent compound because aluminium does not easily lose the 3 electrons. So the ionization energy 1 plus 2 plus 3 is very high. So it prefers to form a covalent compound. So does the other AlCl3. Hence, this satisfies the octet of this aluminium, while the lone pair from here goes to this aluminium, making it a bridged dimeric structure known as Al2Cl6, where these 2 chlorines are called as the bridged chlorine atoms, which are forming a covalent bond with aluminium and a coordinate with the other aluminium of the other AlCl3. This situation is under anhydrous conditions, where there is no bond. So anhydrous AlCl3 is like this. It is a covalent compound and covalent as a BeCl2, also as a polyethylene. Now chlorides anhydrous acts as Lewis acid. Now anhydrous chlorides BeCl2 as well as AlCl3, both of them are covalent. Here beryllium has 4 electrons, here aluminium has 6 electrons, so both are electron deficient. Hence both are Lewis acids, and Lewis acids are the requirement of catalysts in the reactions conducted by Friedel-Crafts. This we would do when we do organic chemistry. Friedel-Crafts reaction is an important part of organic chemistry where you can use beryllium chloride or aluminum chloride as catalyst only because they are good Lewis acids. No other reason for them to act as Friedel-Crafts catalysts. With this, I end the class. We finished the chemical properties of group 1 as well as group 2. With this, we are concluding class. Thank you. Bless you all.